Okay, so I will talk about ion escape at Mars and Earth, and mostly actually about Earth, and there it will be a kind of empirical continuation of the previous talk, so I'm very happy to see that talk. First, we can start out with comparing then the magnetized planet of Earth with Mars and Venus on the same scale, and here we see how much smaller the environments are, the induced magnetospheres of Mars and Venus. And they are essentially smaller than the region of strong interaction in the cusp region, where the connection opens up the magnetic field lines at Earth and allows solar wind, both a cross-polar cap potential drop that we just heard about, but also the precipitation of these soft electrons and protons from the solar wind. And the Earth here is shown also in a cylindrical coordinate system, which leads to these funny field lines of the closed field lines that they go around, and then the open field lines stretch out. And it's quite well known since long that the outflow at Earth and Mars and Venus are quite similar, despite this distance, standoff distance of the solar wind at Earth. But as seen here, that leads to a much larger interaction region, and we have a very efficient interaction in the polar cap, in particular the so-called cusp, which is the most equatable region of the polar cap. And there we see this upflow we just heard about. This is in coherent scatter radar data. The second row shows the electron temperature in the F region, so that's some 300-400 kilometer altitude. This plasma is long-lived and drifts around. The cross-polar cap potential drift sets up a convection that brings fresh plasma in from the lower latitudes. But if you look at the upper row, you see that there's some enhancement of the electron density as well. So there is production locally, and there is an inflow of fresh plasma in what's called the bounder cusp. There you can also see some very, very low ion density or electron densities in the most poleward part, indicating that sometimes there may be a limit on how much plasma there is in the ionosphere. This can be because everything has been flowing out, or because strong Joule heating leads to ion temperature enhancement, which you see in the third row, and this can lead both to upflow but also to enhance recombination. So this is then the starting point. And then we use the same papers here, Bob Strangway's paper from 2005. The upwelling ions must, as we just heard, be heated as well. There's plenty of good studies on this, but because it was just presented, I skip forward pretty fast. If we look at what we see with the cluster spacecraft, we see quite strong wave activity at the oxygen gyro frequency at the highest altitude. So, and the fluxes we see there are similar at the lower altitude seen, for example, in Bob Strangway's fast data. And this means there is a continuous, very efficient heating of these oxygen ions, giving them quite significant velocity, enough that they actually will escape. But at the magnetized planet, this is not obvious. First, we must overcome gravity. Then we must overcome the magnetosphere, because there is the possibility that the plasma is transported to the tail, down into the plasma sheet, and then back towards the planet. And I will come to that in a moment. But there is so much energization of most of the oxygen that we think we can say that all this escape. And that means, if you look to the right, that we have typical escape rates of 10 to 25 to 10 to 26 ions per second. The same, there are two different ways of showing it here. One as the Kp index, and the lower one is the solar wind dynamic pressure. In the lower panel to the left, I'm showing the proton gyro frequency, and I'm showing some empirical trajectories of ions with a lower parallel velocity. There we see that if ions follow such trajectories, they never encounter regions with strong heating, and they remain cold. And that is seen in the data. There are cold ion populations and hot ion populations. but the cold ones are dominated by protons. So it's typically the classical polar wind. I mentioned this with that the F-region plasma is long-lived. So apart from the local production that is flowing out from the cusp, there's also fresh plasma brought in from lower latitudes. When activity is enhanced, the cusp moves equatorward into more sunlit regions, but also there's a stronger drift of plasma into this region. And I think Bob Strangway was the first to try to estimate how big this influx can be, and it's a similar order of magnitude as the outflow actually, but there is also local production. And this can, for extreme events, and if you want to extrapolate this, be important as a limiting case, but there is possibility to look at this at Earth. To the left here, I show example of total electron content data, so-called polar cap patches can form. So this is, you can see how enhanced plasma density are seen stretching into the polar cap, moving along the equipotential lines here, so with the equal speed drift. So there is certainly a possibility to see if this happens during storms as Earth. I'm not sure that polar cap patches has been studied in that way in combination with outflow and escape, but the data should be available. Now I mentioned that it's not certain that ions escape because they reach above escape velocity. That's a very important paper from 2001 by Seki, where they looked at how the outflow in the tail got lower and lower the further back down the tail you got, and an obvious explanation was that it was going down into the plasma sheet and return. But another possibility is that it's further energized, and I would say that the post-cluster picture is that it's further energized and it is rather lost to the magnetopause and into the magnetosheath. But that's another aspect of this return flow in the tail. And first, with the cluster data, we don't see enough return flow to really diminish the escape significantly. That's one thing. And another thing is if we look at the precipitation rates seen by, for example, the DMSP satellite, the Newell's papers, series of papers, I think are the most known, those fluxes are far below the outflow. And one aspect of this is that if you heat the ions enough, this is true even if they're bound by gravity, they can still be heated enough that they will mirror in the magnetic field and not go down. So they just keep bouncing around, and then they are probably eventually lost through charge exchange, but they can also be lost through pitch angle scattering and finally precipitate. And this is true also for the return flux from the tail, meaning that hopefully we can ignore the tail if we want to judge what the total escape is, and that would facilitate things. Otherwise, we would need a very complete picture of the whole circulation in a magnetosphere of an exoplanet or something like that. So just a few words about Mars then, because I promised to do that as well. So it's a mostly unmagnetized planet. There's some crustal magnetization. I will not talk about that, others will do that. It has a comparatively low gravity, meaning larger neutral escape. In particular, important is this dissociative recombination of O2 plus. So what we see at Mars, the most careful study, I think, the biggest study with much data is by Ramstad et al. 2018, where they see that it mainly goes up with the photoionizing flux, the total escape. It actually goes down with the solar wind dynamic pressure. We recently complemented that with a study where we divided all the Mars Express data into periods with a length of 1 Martian year. And we also see a very clear solar cycle dependence. The black line here is the total escape rate. The green line is the F10.7 index. And we made a fit of that, just a simple linear fit, where we also compare with the Ramstad value and another from Richard Lundin. And you can see that it's quite a large spread, but we can get the Mars Express and the Phobos values obtained in a previous mission to be approximately in line. And the large spread is because it's simply difficult to really well constrain the outflow with one spacecraft from such varied conditions. But this leads to the idea that at some planets, it's either production or energy limited, at least in the easiest, the most simplified sense. And Moa Persson showed yesterday that for Venus, it's then energy limited. Work by Schilling et al., which I show here, shows that it's also energy limited at Earth, whereas the Ramsar et al. Study then shows that it is production limited at Mars. So I have some minutes left, so I just end with mentioning a study by Gunnell et al., where we looked at if we use the empirical outflows we see from the polar cap, from the cusp, from in the induced magnetosphere of the unmagnetized planet, that's empirical, but then we calculate sizes of the polar cap and cusp and interaction region for a magnetic field of different strengths. And then we see that we actually don't have the highest outflow for the lowest magnetic field. It's actually increased when we have a weak magnetic field that maximizes the connection. This is reproduced also in some hybrid models. It then goes down, but then there's a second peak when the energy inflow is most important, is maximized. And then if we go to even stronger magnetic fields like Jupiter-like, then the intuitively obvious that there's almost no polar cap left. There's so far to go to between the solar wind and the planet that then the outflow is minimized again. I think Romain will talk about this tomorrow, so you will hear an updated version of this model. So my conclusions are then what I think quite a lot of people already know, that magnetic field does not necessarily diminish atmospheric escape. I have a suggestion for modulus that hopefully you can ignore the tail return flow, but at least for Earth. Wave particle interaction is needed in a self-consistent modeling, as we just heard in the previous talk, and that's difficult to do, but maybe it need not be super accurate, except in limiting cases. It may be enough to provide velocities above escape velocity. But if we want to go really far for really extreme conditions, then saturation of the outflow may occur, and I think more work is needed there. In particular, the circulation in the ionosphere may be important for magnetized planets. And then for Mars, a simple statement would be that I think the low gravity is really the main reason for the bigger loss of that planet. So thank you for your attention.
Thank you very much, Hans. So we are now open discussion. If you have a question, please raise your hand or put on the chat, please. Oh, one question on the chat. I think, the return flow be significant for Jupiter or super Earth?
Yeah, I mean, well, that's a good question. I think it depends on Earth. I think that one reason is probably not important is that even if it goes back to the planet, it will probably charge exchange. You will need strong pitch angle scattering to get it back. But in other environments where they are not maybe so obviously lost after a while, maybe it will be important. And at say Venus, it seems return flow. There is a return flow in the tail there as well, and that seems to be important.